menu to the calculus part. You scroll on down, scroll down, scroll down, scroll down. I'm not, keep going, and voila, E, implicit differentiation. So you hit that. It's just a function. It's for those of you in computer science class, it's just a function that's been written, a procedure that is stored inside the calculator. When we give it the right information, it's going to crank it out for us. So let's just do number 9. Let's do that first part of number 9. It was x squared.
X times x is negative first?
No, I'm sorry. Do I have the wrong problem? Or are you on the wrong section? You're on the wrong section. Right here. There you go. That one right here. X squared plus, now when you type xy, you've got to type what? X times y. You've got to plot it, you've got to do x times y plus y squared equals 1, comma, x, comma, y. You got to tell it what the input variable is, and then you've got to tell it what the output variable is. Hit enter, and it gives you that right there. Now, that might not be the same format, so Tim, we'll just leave that right there. But now if we go to the work that I've done here, here's what I did on that one on number 9. Okay, so I got this. Okay, so derivative of x squared is 2x. This has to be a product rule, so the derivative of x is 1, leave the y alone, plus the x left alone times the derivative of y, which is y prime, and then plus the derivative of y squared is 2y, y prime, and then equals 0. Got the y primes on one side, got the other stuff to the other side. Because let's face it, when you're doing it, think about this, guys. Look up here. If you've got an algebra equation, you got a bunch of x's and you got a bunch of non-x's. You want to get the x's all on one side. You want to get the other stuff over on the other side, right? Well, that's what we're doing here. We want to get the y primes on one side, and when we get the non-y primes on the other side, we factor out a y prime, then we divide. Now, look what I ended up with here. Now, if you could take a negative 1 out of that top, then you'd have 2x plus y, and then the bottom would be x plus 2y, and I think, isn't that what his calculator said? Negative 2x plus y, and then the bottom x plus 2y. So you could use your calculator to check you on these with implicit differentiation, so do it. But again, I've been teaching this for 20 years, and we've been using these calculators for a long time, and that's the first time I've used implicit differentiation on the calculator. So you know what I mean? So it's not really going to be something you're going to need to do. Not like that solve thing where we said you've got to be able to do a solve on your calculator. You're going to need it. Yeah.
Like, how do you know that it's going to be an implicit differentiation?
Anytime it's a mixture of x's and y's. If you have a function that's just y equals and then a bunch of x's, right, then that's just a regular, that's an explicit function. If you've got a mixture of x's and y's, right, throughout the problem, that's when you know it's an implicit differentiation. Okay? All right. Now, let's go ahead and keep going with this, and then we'll talk about just any other practice that you did that you have questions on. So here's the first one on 9, then here's my second one. The thing on this, the thing you got to be careful of on 9 with this negative, I always connect that negative to that x. So I'm going to think of this as my two things when I do my product rule. So I'm going to have 2x for that, and then when I do the derivative of negative x, that'd be negative 1 times the y left alone. And then when I do the negative x left alone times the derivative of y, which is right prime, that way that negative gets carried through there. I don't have to worry about distributing or anything like that. So I always connect that, whatever's in front of that, with that x. Okay, and then this. And so this comes out to be very much the same. Now, Emily asked a question earlier. What happens like at this step right here? Everybody look at this step right here. When you get to this step right here, who's to say whether you're going to keep your y primes on this side or move them over to this side, right? You could do either. But it's kind of like a problem like this. If I've got a bunch of x's, it's like this problem right here. One person might get all their x's on this side, right? So 3 minus 4 would be -1, then you take away 7, you get -7x. This side, you take away 7, you get 3, okay? So you're going to get an answer of -3/7. Okay, another person might say, I'm going to move the x's over here. So then you'd have 6, you'd add 4, it'd be 10. You take away 3, you're going to get 7x over here. And then here you got 7, take away 10 is -3. Do you see how you just get opposites, right? But at the end of the day, see on this one I actually get 3 divided by -7. On this one I actually get -3 divided by 7, but they're the same. I just get opposites on top and bottom. Well, it's the same thing here. So that's number 19. Well, let's just move on to number, let me make one more comment about number 9. So number 9, you were supposed to do the derivative of each one, then you're supposed to tell which curve was which, right? And they said, why don't you take a point like 0, 1 and just plug it in and see what you get? Well, on the first one here, if I plug a 0 and a 1 in for x and y, I get -1/2. Well, one of those ellipses went like this. At 0, 1, it had a positive slope. And then the other ellipse came down. I don't remember. I didn't draw that very good. But then the other ellipse at that point had a negative slope. So this one has to be the one that has a negative slope. Make sense? Okay. And before I leave that one, Tim, let me show you the other thing you can do with implicit. Again, we never really have to do this on the calculator. But just hit escape. I'm sorry. So go to your graph screen, okay, and go to your menu and your graph entry. This is something they just added here about a year ago, actually. Under graph entry, go to relation. Remember I said yesterday if it's not a function, right, like circles and stuff like that, we can do those under relation. So type this in here. Type in x squared plus xy. Good job. See, I said xy, but he typed x times y. That's good because you can't just type xy. Equals 1, and then hit enter, and then it'll do that ellipse for you. So it's pretty cool because graphic calculators didn't used to do that. Desmos on your Chromebooks is a really good graphing tool too, right? But again, we can't use those on AP tests. We can't use computers on our tests, obviously, so you can't do it. Now, and you can do the slope at different points here too, if you needed to. Again, it's not something that is really something you're going to ever have to be able to do, but it is there. Go to the menu now. Go to the menu and then analyze graph, and then dy dx, which is your derivative right there. Okay, and then we wanted the derivative at 0, 1. So just type in a 0. Just type in a 0, Tim. Just type in a 0, hit enter. And see, it gave him that point there. Do it again, because there's 2 points at 0, so that slope is -1/2. I think because of symmetry, go back to menu, analyze graph, derivative. Type 0 again. I don't know why we don't get, I was getting this other point. I'm not sure how, maybe you might have to move it around with your arrows. I don't know if you can grab it or not. But anyway, so it comes out -1/2. It's -1/2 down there. It's also -1/2 up there. I did it on mine earlier. But anyway, we just showed that. We just got that. So just a couple things about your calculator that can maybe help you when you're doing some work on some problems. But, Tuesday, it's all no calculator with the derivative. So you got to be able to do that. All right, let's go to number 19 here. Let's see, I did a little bit of work already for 19 for some people that came in this morning. And when you get to the 19 through 22 section, Max and I were talking, some people, and some other people that came in too were thrown off by where it said find the equation of the tangent line. Remember, the equation of the tangent line is nothing more than to find the equation of a line, and what you need is a point and slope. The key is it's a tangent line, that's a derivative. The derivative is the slope of the tangent line. That's what derivative is. So we want to do the derivative, and of course that's what our whole gateway test is about. Next Tuesday is doing the derivative of all these functions. So any of these functions, we can find tangent lines on these functions because we can do the derivative, right? So you got to do the derivative, and then you just plug your point in to get your slope. So the whole point of this problem is just doing the derivative. So we do our implicit differentiation, which I got worked out here. Okay, we get our y primes on one side, we solve it. Here's the y prime we came up with, or like Emily said, hers were reversed, right? She had them the other way around, like I have it read. Doesn't matter, that's what I was getting at on that other one. Doesn't matter if they're switched around, because basically, instead of getting, like this one, instead of 6 minus 2, 8 minus 3, which would be 4/5, if you've got them switched around, you get -4 over -5, which is still 4/5, right? As long as they're both switched around. So if you had this, or you have this, they're both okay. So in the gateway test, I'll know that, and I'll look at your work, and I'll be able to see it. Okay, then you plug in a 2 and a 2 for x and y, you get -1 slope, so that's all you got to do then, right? I mean, you just, on the gateway test, we'll stop here, right? Gateway test will stop here. But equation line, plug in point, keep your slope, boom, there's your tangent line, that's all you do. So, okay, all right, so, here's 21. Just to go through it a little bit. Now, if this was on the gateway, this would be one of the hard ones, right? This would be one of the hardest ones of the 10. I might pick a hard one for the implicit one, right? Like I said, if you're gonna get an 8 out of 10, you're probably gonna have to do at least one that I would consider, somewhat challenging one, right? Would be what I would think would be some easier ones, some medium ones, some harder ones. This would be a harder one. And the reason this is a harder one is because you got to FOIL this all out, because the whole point, if we're going to get the y prime by itself, we got to have a bunch of terms all written out so we can move them around and isolate the y prime. So it's really just algebra at that point. But this would be one of the most challenging ones I would ask you to do. Okay, so you could FOIL it first. I went ahead and just did the derivative first. So I just said, okay, I got an outer function. So your derivative rules, you still do the same. The only new thing we've added is when you do a y derivative, you stick on a y prime. That's all we've added. So Emily, you see why this is an implicit differentiation. It's just a mixture. It's not a y equals, right? So we're going to do our normal derivative. So we're going to bring the 2 down in front, which is a 4. We're going to leave the inside alone to the first power. Right? Then we're going to times by, and then I'm going to put parentheses here, the derivative of the inside. So now we got to do the derivative of the inside. Well, the derivative of the inside is 2x plus derivative of y squared to be 2y y prime, right? So there's nothing new there, except right there at the end, we did the derivative of the y squared. We had to tack on a y prime to it. But otherwise, that's just your plain old chain rule. This side, we have to do a product rule. Now, I would connect the 25 with the x. Okay? So, derivative of 25x is 25 with the y tacked on. Excuse me, with the y left alone. Plus 25x left alone. Derivative of y is y prime. Now, again, what makes this hard then is we got to get our y primes on one side. And I got a y prime stuck in here that I got to be able to move. Well, so what I got to do is FOIL this. I got to FOIL this out. So at this point, see, the calculus is over, right? I mean, calculus is done on this problem. Everything left now is just algebra 2. That's all that's left, or even algebra 1, I guess you might say, except we don't see y prime. But we just got to FOIL this thing. So it gets to be a mess. Now, I went ahead and took the 4 through this one, just so I didn't have that 4 sitting out there. I could have done the 4 later, okay? But I went ahead and took the 4 through this one. You don't take the 4 through both of them, by the way, right? You're not distributing it. You're distributing the 4. It's like you had 4 times 2 times 3. You don't take the 4 times the 2 and times the 3, right? You take the 4 times the 2, which is 8, and then you take that times the 3. So I'm going to take 4 times that, and then I'm going to take that times that. Okay, I've seen people do that. So I just got to FOIL this, and so it's a big mess, but it's 8x cubed. Outers would be 8x squared y prime. Inners would be 8xy squared. Last time the last would be 8y cubed y prime. Okay, so I just had to FOIL it. And over here I got that. So now the 2 in blue are my 2y prime terms, so I need to keep them on one side. Oh no, I got another. Yeah, there's 3. There's a y prime term there too. So there's 3 y prime terms. So I'm gonna keep them on the left side. So I moved that one over. I'm gonna get rid of these other two terms to the other side, so that's all I did there. Now I'm gonna take out my y prime. I just kind of skipped that step because I was running out of room. So I took out my y prime, which would be 8x squared y plus 8y cubed minus 25x. I'm gonna divide that over there. So my y prime ends up being all of that. Calculator do that? You type that one in the calculator. I thought maybe that's what you were typing in. Okay. Under that implicit thing, you can type that in, and it, I would think, would give you that. Okay, then what's left? Now, in the gateway test, we'd be done. We'd just stop right there. But there's your x and your y. Plug that in, which I did right here. I got 2/11ths for my slope. Well, so now you got a point, 1, 2, and you got the slope, 2/11ths. And there, in the red, there would be your tangent line. Okay? All right. So, that, I mean, I don't have much else to tell you about implicit differentiation. I mean, that's it. That's, now it is gonna come up this year. I mean, there's gonna be problems. I mean, just as we go along, there's gonna be times where this is what we're gonna need to do, right? We're gonna need to do implicit differentiation. So it's not a big deal. It's not a big deal. It's a mixture of x's and y's, and when you do the derivative of y, you have to tack on a y prime. And, and then solve for them. That's it. Okay? So not a ton of practice. I think it was derivative practice number 2, where you had several PDF practices with solutions on them. I think the third one, I think the last one there had a number of them to practice. So as we get towards Tuesday, it'd be good to practice some of those. The book doesn't have very many. We did most of the ones in the book. And page 195 doesn't have any at all. So but you can make them up. I mean, you can just make them up. You just, just do a mixture of x's and y's, and then do it, right? All right. So, any questions on page 195 or from the website or any of those that you would like to see me do for you or help you with? Because we have one new thing to talk about here and go through, and then, but that's it. So, somebody got one?
Some of the website ones, they weren't bad. Most of them.
So which website?
I think it was the one that had the 3 derivative tests.
Yeah. Yeah, I mean, sometimes in class we tend to focus on the hard ones because those are the ones people have questions on, and so you start thinking like every problem is going to be this hard, really crazy, difficult one. That's not true. I mean, hopefully, if you're doing enough practice on your own, like Max said, and you're going through there, you're going, oh yeah, you're getting them. Now, with that said, if we sat here and just threw out 10 of them, how many, we don't probably have time to just do that many, but we can do some if you guys want to here. I mean, whatever you want to see. Getting 8 out of 10 without making some little mistake or something is not that easy. Right? What did I say? Or maybe that was on the video. The typical pass rate is somewhere between a fourth and a third, usually less than half. So we have a total of 30 some students in Calc, 35 to 17. Typically is about the max, but then quite a few second try, third try, so that's still an A in the grade book. So. But the key is practicing a bunch before next Tuesday, because here's the problem. After next Tuesday, we're moving on, right? We're moving on to new stuff during class. You've got to stay caught up with the new stuff and go back and keep practicing your derivatives and try to pass the next time, right? Right now, between now and next Tuesday, this is all we're doing. This is our only focus. So you need to practice a ton of them now, because it'll be harder then, because then you're trying to balance more stuff. Okay, Emily, do you have one?
I think it's 30.
Out of the book?
Yeah.
Read it to you?
It's f of x equals 3e to the sine sine of 2x.
3e raised to the sine of 2x.
Yeah.
Okay, like that. And I just wrote y, but y f of x, whatever, doesn't matter. Okay, everybody try that one real quick, if you haven't tried that one. Now, when you go to page 195, if you just want to start at number 1 and go on down, that's fine, but it's not a bad idea to jump around either, you know. So did you have a thought there, Emily, or something to do with it?
I don't know.
Uh-huh.
Okay, you have to do the outside first.
Which is,
Because they're e to the sine.
well, I mean, 3e to the sine is pretty much the whole thing.
Yeah, so then I don't know.
I mean, well, let's put it this way. The 3 is just a number sitting out in front of this thing, so it's just going to sit there, right? So we're really doing e to the sine 2x. So that's a really good question. What's the outer function here? The rule we're using to start is that rule, right? We're doing e to the u. And the derivative of e to the u is what? E to the u times u prime, right? The inside is this, right? So the derivative of e to the sine x is sine 2x is e to the sine 2x times then u prime, which is the sine 2x, right? So now what's the derivative of sine 2x? It's cosine 2x and then the derivative of its inside, but we've done that so many times that hopefully we just know, hey, I'm going to kick out a 2. But what you're really doing is the derivative of the inside, which is 2. But so it's just going to be then 2 cosine 2x. Now, the 3 and the 2 need to get put together. This needs to be written then with 6. And then, so Emily, talk to me. What doesn't make sense on that, or does it? Or
Yeah, I guess I get it. I just didn't know what the outside and what the inside
yeah,
was.
it's weird. It's maybe instead of thinking outside inside so much, it's just like this is e to some stuff, right? This is e to the u is what we're doing, right? And think of it that way. The u is the inside of it, right? But you're right. When you've got ln of some stuff or sine of some stuff, there's always parentheses around it, so you kind of tell what the inside outside kind of is. But here the outer. Think of it this way. If you were going to plug a number in for x, where do you always plug it in? Well, you plug it into the inside, right? So if you were going to plug something in, what order would you do it? You'd plug a number in here for x, then you do the sine of it, and then you do e to that, right? So the last thing you do, it has to be the outside. Does that make sense? I mean, so like if I'm doing a bunch of stuff squared, I'd plug stuff in, and then I would square it. The outside is the square, right? Maybe that's a way to think of it too, okay? So that would be your answer for that one right there. Yes. Read it to me. Okay. Okay. So this is one of those that they're trying to make you really think about what's going on here. E to the pi, what's that? The key to this is recognizing that's just a number. Yeah. So we're not doing a derivative rule on the e to the pi. That's just like if there was a 7 sitting out there. So we're just going, that e to the pi is just going to hang out there. Okay. Now, what's x to the e? Well, that's x to a number. So that's like doing x cubed or x to the 4th or whatever. Right? That's just x to a number. So what's the rule for that? Bring the number down and subtract 1. Now, I don't anticipate giving you this one because we don't usually see numbers like that. But if I did, I would think you'd need to put this together, right? I mean, what's e to the pi times e? No. No. Yeah, what's x to the 7th times x? That's x to the 8th, right? You add the powers, right? So e to the pi times e to the 1 is e to the pi plus 1 times x to the e minus 1. That's really what that answer ought to be, right? You're multiplying and the bases are the same, you add the powers. Right.
Isn't this the product rule?
No, because e to the pi is just a number. E to the pi is just 2.7 to the 3.14. Now, okay, Emily, time out. Could you do the product rule? Yes. But here's why I wouldn't. Because people mess it up. Because, all right, if we want to do the product rule says what? Derivative of the first, right? What's the derivative of e to the pi?
Pi.
No. 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 Because e to the pi is a number, right? What's the derivative of a number? What's it? 0, right? So the derivative of e to the pi is 0 times x to the e left alone plus e to the pi left alone times the derivative of x to the e. What's the derivative of x to the e? E times x to the e minus 1. So see how that would just disappear and then we end up with the same thing anyway, right? But the reason people mess that up is because they forget that when you do the product rule, you got to do the derivative of a number. Now, right? So that's if we're doing the product rule. Now, if we do it the way we did it, we said, hey, when you have a number times a function, that number just sets them. Okay? All right. Another one.
Maybe 42.
I hope I can. What is it?
Cosine cube to x to the 4th. X, no 2.
No 2. Like that?
Yeah.
Now, do you hear how Will read that? He said cosine cube, and then did you say 2, or why did I write it 2?
Is it 2d?
To the x to the 4th or something, right? Now, just in reading it tells me that, because how should this one be read? And I don't, except the to the, because it's not cosine raised to anything, right? It's x to the 4th. There it's But how should this be read? This is cosine of x to the 4th, all cubed, or cubed, or whatever, right? You see what I mean? Because cubed is the outer function here. But I know why Will read it that way. We always do that. We all say sine squared, cosine cubed. We always say it that way, right? But the problem with saying it that way so much is we kind of forget what it really means. It's cosine of x to the 4th, all to the 3rd power, right? And if we don't write it like that, or at least think of it like that, we're probably going to mess it up when we do the derivative. And that's why when I was a trig teacher many years ago, before I started teaching calculus, I did this notation all the time, didn't think a thing of it. I started teaching calculus and it started driving me nuts. And so now I don't like that notation because in this class it kind of causes us some grief. Okay, so what are we going to do with to start? We're going to bring that 3 down in front. We're going to leave that inside alone, cosine x to the 4th, squared. A lot of times we forget that. It's really easy to do that. We bring that 3 down, we got all this messy stuff. By the time we get done writing it out, we forget. So that's why it's not a bad idea. Sometimes you go 3, da-da-da, squared, and then you go back and fill in the inside, right? Because you're leaving the inside alone. Anyway, times what? The derivative of the inside. Well, the inside's kind of messy, so I usually put a big set of parentheses because I know it's got to go in there. Right? Now, I don't have any plus signs in here, so that's a good thing. That's going to, usually the plus and minus signs what mess me up. I really need my parentheses there. So now we're doing the derivative of the inside, which is the red part. Well, how do you do that? Well, you do the outside first, which is negative sign. You leave its inside alone. And then times, I'll put another set of parentheses, and then the green part, right? Your derivative of its inside, which is 4x cubed. Now, this is where, whenever you get a problem like this, it's got all this kind of stuff strung out here. I think it's good that then you just got to step back. You got to look at the whole thing, and then you got to decide, okay, what can I put together? What can I? Now, what I notice here is these things are all just multiplied. It's like A times B times C times D times E. I can just rearrange those however I want. Okay, so this 4, this negative, this 3, I need to put those together. Okay, and then it becomes a cosine, and then I can use my notation if I want. I can do cosine squared. I can put that as cosine squared, but I can leave it like this too. I don't care. And then the sum, x to the 4. Oh, and what did I forget? I forgot my x cubed. You know, I would probably put that around here with the 12. So I'd have negative 12 x cubed. Probably be a good place for that. Okay? That would be on the tough side of things, probably, just because it was like a double chain rule, you know, inside and then some more inside. All right? One more. 44. What do you got? It just says it like that. Now, the thing about e to the x squared, whenever they do that, it always bugs me a little bit. If they don't have any parentheses on that at all, assume that it's that. Okay? Because what would e to the x quantity squared be? That's e to the 2x, isn't it? Right? Because a power on a power, you multiply. A power on a power, you multiply. So e to the x quantity squared would be e to the 2x, okay? So that's not the one we have here. We have this, okay? So if there's no parentheses on that, assume it's that. Okay, so we start on the outside. So what's the derivative of tangent? Make sure you're going back to those derivative rules and looking those over, right? Especially the ones I starred. Now b, you know, a different base like 2 to the x or log base 2. Tangent is secant squared. Cotangent is, and they're really related. I mean, tangent is secant squared. Look at cotangent. It's negative cosecant squared. So they're very similar. And then secant over here, secant, the derivative is secant times tangent. And then, of course, times the derivative inside. But once you got secant memorized, then cosecant's very similar. It's negative cosecant cotangent. Okay, so they're not that hard. You just spend a little time doing them. You don't see them very often, but you need to know them. So it's secant squared. We leave the inside alone. Again, we could do secant the whole thing squared because that's what it really means. Times the derivative of the inside. Now again, I'm just going to put a big set of parentheses here just in case I need the space. So it's going to be times the derivative of the inside, which would be the red part here. So now I'm doing that. Well, remember, that's just like the one Emily asked about earlier. That's just like e to the u, right? So what's the derivative of e to the u? It's e to the u. So that's going to be e to the x squared times u prime. Well, what's u prime? The u is x squared, so the derivative of that is 2x. Now that one, I don't think you need to rewrite that at all. I mean, now it's just rearranging. You're not really putting anything together. I think the best version of that would be the 2x around front, probably the e to the x squared with it, and then maybe the secant squared at the end. But it doesn't matter here because that's just rearranging. You didn't put anything together there. Right? And again, we've done several in a row that didn't have any pluses in them, you know. So just remember, if you get like a 2x plus 1, that usually is in parentheses, kind of as a quantity. You got to kind of keep it together. For example, if this would have been x squared plus x up here, well, then you'd have had a 2x plus 1 here, and you'd have needed parentheses around that, right? That kind of thing. So just be careful of that. Okay, we can get one. All right, let's go on. Let's go on to, now we didn't do any quotient rules or anything, so keep that in mind. Maybe at the end of today, if you want to see when we can do that, or Monday. Monday's going to be a lot of practice time. I'll let you guys throw some at me up here, and we'll work them together or whatever. But we do have one new thing to talk about here, and it has to do with these last three rules over here: arc sine, arc cosine, and arc tangent. Okay. Now, I am going to have you take some notes here. The first part of this, you probably can just follow along. I'm not sure you need to write down these notes. But before we can make sense of arc sine, arc cosine, arc tangent, we need to review inverse functions a little bit, because inverse trig functions, because we're going to need this in some things we do later. But as far as the gateway test next Tuesday, it's really just this easy. They're just functions. Arc sine of some stuff. So whatever the stuff is on the inside goes right there. And then times the derivative of the inside, whatever the stuff is. So arc cosine of some stuff, it's exactly the same as arc sine, except that negative. And arc tangent is this, which is very similar, doesn't have a square root though. So really, you're just going to have to memorize these formulas and use them, but that's not going to be that hard. Okay? But what I feel like we need to go through is, where do those come from? Why do those look like they do? Right? I think that's important, and it's something we're going to see in some problems later on. So, here we go. All right, so this part I wouldn't bother writing down. Okay, so what do we know right now? What do we know right now about inverse functions? Well, several things. We know this I would say would be maybe two of our most famous inverse functions. Right, x squared, square root of x, and e to the x and natural log x. Okay, here's e to the x right here. Graph looks like this. Here's y equals x squared right here, parabola. Now, remember this part of inverse functions, you interchange the x and the y, right? Interchange the x and the y. So if I take y equals e to the x, I interchange the x and the y, and then I try to solve for y. That's what we usually do in inverse functions. So if I try to solve for y, do the log of both sides, get ln x. Here, the y would come down in front. Ln e is just 1. So you get y equals ln x. Okay, that's why they're inverse functions. Over here, if I interchange the x and the y, I get x equals y squared. I do the square root. I get plus or minus square root of x, so sideways parabola. Now, the problem with that is that's not a function. Now, on natural log, it is, right? So it's not a problem. So here's my e to the x. And then, of course, remember, mirror images, right? Inverse functions are mirror images like this. Here's square root of x here. Here's x squared here. Again, mirror image kind of thing. Okay? All right, so that's just a basic thing on inverse functions. All right, now, here's another thing about inverse functions. They cancel each other out. They undo each other. So, like if I have ln of e to the x, I just get x, right? Because x could come down, ln e is 1. Or if I do e raised to the ln x, again, I just get x. Okay, inverse functions undo each other. Now, again, we do have to be careful with square root. We've talked about this. Square root of x squared, does that equal x? Well, it turns out it does, because if I have square root of 3 and then square it, that does equal 3. Can I have square root of negative 3? I can't do square root of negative 3, right? So square root of x is, by definition, square root of x is always positive, and then I square it, right? That's going to be positive. And so x starts out positive here, right? By definition, x has to be positive if we're doing real numbers. X has to be positive here, so x has to be positive when it comes out. So that's fine. So that is true. But what about this one? This is the one we said isn't true. Couldn't x be negative here? But can x be negative here? You do the square root of a number, you just get the positive, right? Square root of 9 is 3. Square root of 16 is 4. Okay? So here, this is not necessarily true. It actually turns out to be that, right? My point is, sometimes you have to restrict the domains. So they undo each other, kind of, mostly. They undo each other, right? But you might have to make some sort of adjustment for the domain. Okay, just a consideration. All right. So now let's talk about trig functions when it comes to inverses. So if we start with y equals sine x, remember, you put angles into sine x. Now, because remember, if we're probably the most common thing that people struggle with the inverse trig functions is this: the inputs and the outputs. Now, remember, when we do inverse functions, we're interchanging the x and the y. We're interchanging the inputs and outputs. So it's important to understand when we do sine of pi 6, we do sine of pi halves, we do angles, we put angles into the trig functions, right? And we get out values. On the sine, we get values. I'm going to call them values, negative 1 to 1. Well, when we interchange our x and our y, we've now changed that, right? We've reversed that. Okay? So the y are now angles, and the x are now our values. And then when we do, and the way you undo this, and some people say, well, you divide both sides by sine. No, you don't divide by sine, that's not times. What you do is, so when you interchange your x and y and try to solve for y, you have to do the inverse of sine to both sides. You do the arc sine of both sides. So that's where this inverse comes. But so what you got to notice is, we've switched our inputs and our outputs now. Our inputs are now values from negative 1 to 1. And our outputs are angles. So when I ask you for the arc sine, so a typical problem would be, what's the arc sine of 1/2? What's the arc sine of 1/2? Pi 6, right? It's like the reverse. I'm saying, what angle for sine gives me 1/2? Well, sine of pi 6, right? So arc sine of 1/2, we have pi 6. So it's just like backwards, right? Instead of saying, what's sine of pi 6? You say 1/2. It's arc sine of 1/2. Now the problem is, if you go to the unit circle, is pi 6 the only time you get 1/2? No. Right? You get 1/2 over here at 5 pi 6. And you get it around here again at 13 pi 6, right? And right, there's a different. Well, we can't have that with a function, right? We can't plug in a half and get out a lot of different answers. We got to get out only one answer. I think in trig class, did you use a capital A sometimes for arc sine? Do you remember that in trig class last year doing capital A? We used to do that. Lowercase a meant you could get multiple values out, and then uppercase a meant just, well, okay. So when we treat arc sine, we want to treat it as a function, so we only want to get one value out. Well, what we have to do, if you think about the sine graph, it passes the vertical line test, right? But if you do the inverse, if you do the mirror image, it goes like this, right? That would be the invert. That would be the mirror image of that. It's kind of like the sideways parabola. It's not a function. The parabola is, but the sideways parabola is. So if we do the inverse function, if we do arc sine, it would look like that. Well, it doesn't pass the vertical line test. So what we have to do is we have to restrict it. We have to say, let's just take this piece right here. That gives us all of our different values. And so it just goes like this. So we just take this. And that goes negative pi half to pi half. So what we do is we're just taking this quadrant and this quadrant. So first quadrant's all of our positive sign values. Second quadrant's all of our negative sign values, right? From negative 1 to 1. So that's why we get pi 6. Type it into your calculator. Tim, do that for us. Everybody else do it. But go to your calculator screen, Tim. And just go the calculator screen. Okay, and now just go to arc sine, which is a negative 1. I hate using that, but that's what it means. It doesn't mean reciprocal. It doesn't mean 1 over. It just means arc sine. Do arc sine of 1/2. 1 divided by 2. Okay, and you get pi 6. Okay, now put arc sine of negative 1/2. Now notice, you don't get 11 pi 6, right? You get negative pi 6, because we're restricting it between negative pi halves and pi halves. So these two quadrants, but we're going this way, and we're going this way. We get negative pi 6. Okay, now let's do an arc cosine. But what would arc cosine of 1/2 be? Would that be pi thirds? What about negative 1/2? Where are negative cosines? Positive is in this quadrant. Negative is this quadrant, right? So what would you get there? So pi thirds over here, that'd be you're not going to get negative pi thirds, right? You're going to get 2 pi thirds. Did you do it, Tim? Do yeah. See, arc cosine you get pi thirds, and arc cosine negative 1/2 you get 2 pi thirds because your negative value. So it doesn't mean you're always going to get this a positive angle, negative angle, right? It's the quadrature. Okay, so cosine. So cosine, our cosine, we would be restricted between 0 and pi. We would just use quadrant 1 and 2 because that gives us the positive and negative cosine values that we need. So we restrict it. So it's kind of like that square root thing where we restrict it. Okay. So does sine of arc sine of x always equal x? Yes. But does arc sine of sine of x always equal x? And then that is no, right? Because if I put in, what do we say, 11 pi 6, where's 11 pi 6? Right over here, right? 11 pi 6 is right over here. If I do sine of 11 pi 6, what do I get? Negative 1/2. Negative 1/2. If I do sine of 11 pi 6, I get negative 1/2. What did we just say the arc sine of negative 1/2 was? Negative pi 6. So we put in 11 pi 6, but we got out negative pi 6. You see what I mean? So this one, not always going to be true. It's like that square root thing where we had to do the absolute value. This one always would be true, right? We do arc sine of, well, we can't even put in 11, right, pi 6 into here. We got to put in, we do arc sine of negative 1/2. We're going to get negative pi 6, right? Then you do sine of negative pi 6. Negative 1/2, right? So if you put in negative 1/2, you're going to get out negative 1/2 on that one. That one's always going to work. But this one isn't always going to give you that because arc sine is going to. Okay. So again, just something to be aware of on trig functions. Not going to be a big deal for a derivative test, but it is going to come up later on in some stuff that we do. Okay. So I already had some questions here. Arc sine y, so we already answered those, so we're not going to worry about that. Okay, so these are some problems you did last year in trig. Again, don't worry about writing these down right now. But if you had to do a problem like this, what you did last year in trig is you made a triangle. Okay, what angle has a sine of 3/5? Well, wouldn't that be the angle that's sine of 3/5? SOHCAHTOA, right? I just learned. Mrs. Linder just told me this. Oh God, I don't know if I can remember. I shouldn't probably say this in high school, but she said this how she did. Some old hippie, God, I gotta find out from her what that was. She's upstairs. I'm gonna find it. Some old hippie called another hippie. It was, we made fun of her because we said, because she was born she lived in the 60s. She was around in the 60s. But, gosh, dang it, what was it? Okay, I'll find it. All right, so anyway, the sine is 3/5, and then what's the cosine of that? Well, you gotta do your triangle, right? And so the cosine is 4/5, right? The cosine of the angle whose sine is 3/5 would be 4/5, right? You do the triangle. Okay, because we're gonna see that here in a minute. Now, what did we just get done saying? The arc sine of pi 6. Well, what's sine of pi 6? 1/2. What's the arc sine of 1/2? Pi 6, right? But what if we do 5 pi 6, which is over here in quadrant 2, right? What's the sine of 5 pi 6? Also 1/2. What's the arc sine of 1/2? Pi 6. Pi 6, not pi 6, right? We always get that one in either first and quadrant. So again, just to emphasize, we don't always get the same thing. All right, now, how's this relate to derivatives? Okay, so derivative, so if you had y equals x squared, you'd have this 0.39. If you take its inverse, it's going to be the 0.93, right? Because you interchange the x and the y. All right? When I do the derivative, I get 2x, I plug in a 3, I get 6. So the slope at 3, right, would be 6. If I do the derivative of x to the 1/2, I get this, x to the negative 1/2, which goes down the bottom. And if I did the slope here, so the slope here is 6. If I do the slope here, I get 1/6. But notice, it's not the slope at 3, it's the slope at 9. In other words, on the inverse graphs, they're not the same point. That's the difficult part of this. The slope at one of them is related to the slope at the other one. They are always reciprocals. It's not a coincidence that we got 6 and 1/6. They're always going to be just reciprocals, not opposite reciprocals like you do when you get a 90-degree angle, but just reciprocals. But they happen at the input of one and the output of the other, right? I mean, or the input of this one and then the output of this one is the input of that one. Does that make sense? Because of that swapping thing. Okay, so we got to keep that in mind because I'm going to show you a problem here in a minute that shows up on the AP test all the time, and I'm gonna pull that up for you. We're gonna do that, and it's gonna involve this opposite or this flipping thing with the slope of this one at 3 is the reciprocal of the slope of the other one at that output value at 9 because of the interchange. Okay, all right. So anyway, this is the part you could write down. Okay, this is the part you could write down. This is the part that's going to lead us to our rule. All right. So it's true to say that the sine of the arc sine of x equals x. That's the one we said would always work. So if I put in a 1/2 there, arc sine of 1/2, if I put a 1/2 in for x, because you have to put in a value between -1 and 1 for arc sine. So if I did arc sine of 1/2, I would get pi 6. Sine of pi 6 is 1/2. Okay, so sine of arc sine of x is equal to x. Now, I'm going to do the derivative of both sides. Let's do the derivative of both sides. Since sine and arc sine are inverse functions, this is a true statement. I'm going to do the derivative of both sides. So how do I do the derivative of sine? Well, I do the outside first. So that would be cosine. I leave the inside alone. Arc sine x I leave alone. Okay? Times the derivative of the inside. I don't know what the derivative of arc sine x is. So I'm just going to put arc sine x prime. Okay, I'm just going to put arc sine x prime. That's what I'm trying to figure out. I'm trying to figure out what the derivative of arc sine is. And then equals 1. The derivative of x would just be 1. Okay, with me? So I just did the derivative of both sides. Now, I want to know what arc sine prime is, so I'm going to divide by this other thing. So I got 1 over cosine of arc sine x. Right? All right, now. So you might think, well, I just stop there. Okay, that's the derivative. Well, the problem is that's not a very useful. That's not going to be a very useful derivative. We can rearrange that. Okay, can I go on? All right. So we got arc sine prime. So this is what you just had written. Okay, this line is the same thing you just had written. Okay, so arc sine prime is equal to this. Okay, now I probably should erase some of this. I should have made this a little more secret. So remember the SOHCAHTOA thing we were just doing a minute ago? Right? So when I look inside of here, arc sine x, that's like saying what angle has a sine that's x? Well, wouldn't it be this triangle right here? Opposite over hypotenuse? X over 1? Right? Remember we did the problem a minute ago where we said arc sine of 3/5? Remember that? And we put a 3 and a 5, and then we wanted to know the cosine of that, and it was 4/5, right? So we just had to finish the triangle. So what I need is that, right? Well, what is that? Well, I know that squared, question mark squared, plus x squared has got to equal 1 squared, right? Would you agree with me? And so question mark squared is equal to 1 minus x squared. Agree with that? So the question mark has to be the square root of 1 minus x squared. Agree? So this has to be the square root of 1 minus x squared. Right? So the angle that has the sine that is x would be this angle, and we want the cosine of that angle. Well, the cosine of that would be adjacent over hypotenuse. So this bottom just turns into that. And so there is where that comes from. That's where our rule comes from for the derivative of arc sine x. Okay, that's where the derivative comes from, that it's 1 over the square root of 1 minus x squared. And if we repeated that with cosine, we see it was a -1. If we repeated that with tangent, we see what we would get. Okay? Because on tangent, what you'd have is you'd have arc tan x here, and you'd have opposite over adjacent, so it'd be x over 1, and so then it'd be 1 squared plus x squared equals question mark squared. Wait a minute, so no, that's not right. Oh well, forget it. I thought quickly we could see that, but actually it's not going to be that quick. So that's where the rule comes from. So, bottom line, a little bit of review of inverse functions, but the bottom line is we just have to know these rules. Okay? Now, where is that problem? I'm going to show you that real quick, then we'll do a couple quick examples. Okay, give me a second. There it is. All right, this is a great example of a problem where they would, this is not going to be on our gateway test next week. This is a great example of an AP test problem that we always struggle with. So I found some examples that I'm hoping as we go through the year can get us. But this is saying y is equal to x cubed plus x. Okay, so you can write it down. You don't have to write it down right now. It's not a bad idea actually though to do it. And what they're saying that is f. That is the f function. Okay, they're saying that is the f function. What they want is g prime of 2. And they're telling you that f and g are inverses. They're telling you that f and g are inverses. Okay? So you would think, so what did we learn about inverses? We learned that their derivatives, their slopes were what? Remember the 6 and 1/6? Reciprocals. So inverse functions have derivatives that are reciprocals. Now, normally you'd say, well, we'll just interchange the x and y. Well, the problem is so the first thought is, well, let's find what the g function is. Before we can do g prime of 2, we need to know g prime of x, right? Remember how much we said that? Well, you say, well, let's find the g function. The problem is, if you interchange the x and the y, you can't solve for y. You get x equals y cubed plus y. There's no way to get y by itself then. You can't get y by itself. So, that's not an option. So what we want to do is we want to do this. We want to find f prime and then do the reciprocal for g prime. The problem is it's not going to be f prime of 2. Let's do f prime of x here real quick. F prime of x is 3x squared plus 1. We can't just do the reciprocal of that. That doesn't work either. Okay? We want to find g prime of 2. So the tendencies want to put a 2 in here for f prime. Well, why can't we do that? Remember the square root thing that we did on x squared? We did the slope at 3, but on square root it had to be the slope at 9. Remember that? It was the output. So in other words, on the f graph, on the g graph, we want g prime of 2. We want to do it at this point, 2 comma something, right? Well, that means on the f graph, it's something comma 2. Does that make sense? So what we need to know is we don't want to put a 2 in for x here. What we need to do is put a 2 in for the output here. We need to see where x cubed plus x equals 2. Right? Now the problem with doing that is that's not something we're going to be able to easily solve. So this would probably be a calculator one. Sometimes it's one we can easily solve. This would probably be a calculator one. So we would just do a solve right now. So go ahead and type it in there, Patrick. We would do a solve right here. of x cubed plus x equals 2. Is it 1? That looks like it should be, right? Actually, in your head, 1 plus 1 is 2, right? 1 cubed. Yeah, all that. Yeah, so much for not easily solved. Yeah, that was pretty easily solved. Well, sure, once we knew the answer, it seemed easy, right? But actually, we probably could have looked at it. If I'd have thought about it, then we probably could have. But, so this means on the F graph, you get the point 1, 2, which means on the G graph, you'd have the point 2, 1. So what we can do is find f prime of 1. Well, that'd be 3 plus 1, which is 4, right? So the slope of f at 1 is 4. So if you want to call that its mirror point, the 2, 1 would be its mirror point. So the slope at 2 would have to be 1/4. And so that's how we would work that problem. And that's how you work that problem every single time. Every single time, that's how you work that problem. When they give you an inverse function and ask you for g prime of 2, but all they give you is the f graph, well, you need to find f prime at not 2, but at its mirror point. So if 2 is the input on this graph, it means 2 would be the output on this graph. So you got to set that output equal to 2, find the input, which would then be where you find the slope of that one, and then you do the reciprocal, you get that. Okay, so that goes back to that thing I showed you with square root and x squared. Okay, so anyway, I wanted to show you that problem. Last thing, let's just do a quick example. Let's get focused back now on what your homework would be like. So your homework would be something like this. Okay, you've got arc tangent of 3x squared plus sine x. Okay, and you're supposed to find y prime. Right? So y equals arctan of 3x squared plus sine x. Now, what's the rule on your homework sheet or on your derivative sheet? What's your rule? This is an arctan u is what this is, right? So what's the rule for arctan? It's 1 over 1 plus u squared. Arctan doesn't have a square root. Arcsine and arccosine have a square root. Arctan doesn't. And arctan has a plus instead of a minus. And then times u prime. Right? So you just follow the rules. So it's really quite easy. With all this kind of tricky inverse trig stuff we've talked about today, actually doing these derivatives is not hard if you know the rules. So it's 1 over 1 plus all of that stuff squared, and there's no reason to FOIL that out or anything. There's no reason to FOIL that out. I'm not going to make you do that. Times 6x plus cosine x, just like that. What's that, Max? Say it louder.
Around that.
Do we? Every single one of you, your skin should have just been kind of like goosebumps, right? When I wrote this, that should have been bothered Max because he said it right away. Yes, that is horribly wrong what I just wrote there. Now, if you wrote it and then remembered, that's great. That has to be in parentheses. That's what I was telling you earlier with plus signs and stuff. When you do the derivative of the inside, yes, that has to be in parentheses. Now, it'd be better to just put it up on top then in your final answer, but it doesn't matter, right? You don't have to. You could leave it just like this. Okay? And this is what I was saying the other day with a lot of times, we do all these problems, we have to do some simplifying and stuff. A lot of times you don't. I mean, there's nothing to do there. You just stop right there. Okay? But yes, gosh, that's got to be in parentheses. And I'll guarantee you that people are not going to do it. If you're going to put a big old dot there, do you think that's good enough? It's not. Okay? Got to be in parentheses. So that's it. I mean, that's all that's really new today. And there's nothing new to do between now and Tuesday, but practice, practice, practice. So 3.4, there's a few homework questions about arcsine and arccosine. Some of them have to do with kind of these trig values and stuff. I wouldn't get too worked up about those questions. I mean, but I still think it's good to do some of that. What do I got? 1 through 6. Yeah, which are just some trig kind of unit circle kind of questions. There's a few with that triangle I did with the 1 and the x and the square root of 1 minus x squared and all that. But really when you get to 13 where it starts saying find f prime of x, that's where it really gets kind of important. And then there's 37 through 39 kind of talk about some of that we talked about earlier as well. Okay, so we talked about all those things. But so 3.4 homework and lots of practice, because this weekend is really your time, I think, to do tons of page 195, the websites. Come with questions on Monday before school or for class time. Come with some that you struggle with, you're not sure if you got them right, you want to look at them. Don't forget quotient rule ones. Okay. Hopefully by Monday night, all you're having to do is just kind of some last minute brushing up and so forth. I think get a study group together, practice a bunch of them, compare notes, whatever. But this is a real opportunity for you to get a 30 out of 30 in the grade book. All you got to do is get 8 out of 10 right.